Types of energy. For the sake of clarity, we shall limit ourselves to two types of energy that an object can possess among many others. These are kinetic energy and gravitational potential energy. Let's look at these one at a time. Kinetic energy, the energy possessed by an object by virtue of its speed. This is why it is also called the energy of motion. It can be shown mathematically that this energy is directly proportional to the mass of the object and also directly proportional to the square of its speed at the instant of measurement. In daily life, we see that objects in motion displace other objects only when they come into contact. For example, a moving marble displaces a stationary marble. A bullet displaces a stationary target. In all of these cases, we must remember that while the moving object possesses energy, it is not doing work unless its mass or speed change due to its interaction with another object or objects. In other words, a bullet moving through free space with unchanging speed possesses kinetic energy, but it is not doing work. A planet revolving around a star possesses kinetic energy, but it is not doing work. On the other hand, a billiard ball that slams into another billiard ball is doing work as it is losing speed and thus losing kinetic energy. This loss becomes a gain for the other billiard ball, which was previously stationary but is now moving. Thus, it is very important to remember the distinction between possessing energy and doing work whenever we analyze such situations. Gravitational potential energy. When we lift an object through a height, we notice that work has to be done. The object moves in the vertical direction under the influence of a force exerted by us. The object placed at a height now has a form of energy by virtue of its separation from the earth. This energy is hidden or latent. There is no change in the physical property of the object. For example, water stored in a mountain dam is chemically and physically identical to the water flowing in a tap or stream. But due to this energy, the object now has the potential to do work. An open dam causes a powerful flow of water. A rock pushed off a cliff will start moving at great speed. Thus, this kind of energy is known as gravitational potential energy. It is important to note that gravitational potential energy exists only because gravity exists. We perform work on an object by moving it against gravity. The work we do gets stored in the object as potential energy. The mathematical definition. Consider an object of mass small m displaced by a height small h against an acceleration due to gravity small g. The force exerted on the object is F equal to mass multiplied by acceleration due to gravity. The height through which the object moves is the vertical displacement. Thus, work done is force multiplied by displacement. The force is mg, the displacement is h, which means that the product is m multiplied by g multiplied by h. It is important to remember that work done due to gravity is independent of the actual path the object takes and dependent only on the initial and final positions of the object. What this means is that you could go from the first floor of a building to the second or the third floor by any route of your choice. The total change in your potential energy would remain the same irrespective of the path that you took to get to the destination. The law of conservation of energy. It is important to remember that energy is indestructible. It may change its form again and again, but if we search diligently, we will find that the sum total of all forms of energy remains the same. This truth was encapsulated in a law, the law of conservation of energy, which says that energy can only be changed in form. It can neither be created nor destroyed. Alternately, we may also state the total energy of a system remains conserved or unchanged. In the words of the famous author Arthur C. Clarke, Mother Nature is the ultimate accountant and she always balances her books. Let us understand this law in an application. We shall limit our discussion to kinetic and potential energy of an object. It can be seen that when a ball is thrown upwards, the force being exerted on the ball against gravity, thus work is done on the ball by us at the instant the ball leaves our hand. Its energy is now entirely in the form of kinetic energy because the ball is in motion. As the ball goes up, it is moving against the force of gravity through a vertical displacement h. Thus, the ball is doing work. As a result, its kinetic energy will decrease. However, we notice that at the same time, the ball is also increasing in height. As a result, the potential energy is increasing. This is a very simple example of kinetic energy changing into gravitational potential energy. At any point in its journey, the loss of the kinetic energy is balanced precisely with a gain in potential energy. This means that the sum of the kinetic energy and the potential energy at any point in the journey of this object will remain unchanged or a constant. Let us consider a few other examples of how this law works. As we mentioned earlier, a planet which is moving around a star has energy but is not doing work. But what does that really mean? The planet is clearly moving through space. Its displacement from the star remains unchanged. So the potential energy with respect to the star remains unchanged because the radius of its orbit remains the same at all points. Since the radius of the orbit is not changing, the height of this planet above the star remains the same. So there is no change in its potential energy. Also, the planet is moving with constant speed. It does not matter where you check the speed of this planet, it always remains the same. Which means that neither the kinetic nor the potential energy of this planet are changing. Which means the planet is not doing any work. We just learned that the kinetic energy of an object is equal to half multiplied by the mass of the object multiplied by the velocity squared at that instant of time. Let's take a closer look at this formula and how it came into existence. If we refer to a previous chapter, we know that the position and the velocity of an object can be linked using a particular equation, which is v square minus u square is equal to 2as, where v is the final velocity of the object, u is the initial velocity of the object, a is acceleration, and s is displacement. Now, if we perform a small shift here, we can see that we can take a to the opposite side. So, we have a new equation, v square minus u square upon 2a is equal to s, since s is displacement. We know that the work done is equal to force multiplied by displacement. And for an object which is moving under the influence of gravity or an acceleration, the force exerted on the object is equal to mass multiplied by acceleration. So we can create a new equation for work. Since work is equal to force multiplied by displacement, let's substitute these values. Let force be equal to mass multiplied by acceleration and displacement be equal to v square minus u square upon 2a. If we cancel out the like terms in the numerator and denominator, we get a brand new relationship, which is work done is equal to half multiplied by m multiplied by bracket v square minus u square. If we assume that the initial velocity of the object was 0, we can simply remove it from the equation, and that brings us to the familiar formula: kinetic energy is equal to half multiplied by mass multiplied by the square of the velocity at the moment of measurement.